So welcome again, all of you. Great to see you here for this second EuroTechTalk. My name is Anita. I'm the communications manager of the EuroTech Universities Alliance, in which frame we organize these talks. Like I said, it's only the second one, so it's a rather new series. And yeah, we invite for these talks, not just one, but two speakers from our partner universities for them to present their projects they're working on together or interesting new findings that they came across. So I know that many of you already, well, you are from our member universities, but I know that also quite a few people signed up from outside of EuroTech. So welcome also to you from industry, from other academic institutions. For your benefit, maybe 2 sentences about the Alliance. So our Alliance is an alliance of 6 universities of science and technology. And they are the Technical University in Denmark, EPFL in Switzerland. We have École Polytechnique in Paris in France. We have the Technion Israel Institute of Technology in Haifa, Eindhoven University of Technology in the Netherlands, and the Technical University of Munich in Germany. And today I'm very happy to welcome our 2 speakers, which are Professor Katrin Wudy. She holds the professorship, now I need to look at my notes, for laser-based additive manufacturing at the Technical University of Munich. And she's the coordinator of the project that she and Professor Fadi Kizel are going to present to you today. Fadi Kizel is from the Technion in Haifa, and he works for the Department of Mapping and Geoinformation Engineering. And today's Tech Talk is about their new project that just received funding called InShaPe. And this stands for Green Additive Manufacturing through Innovative Beam Shaping and Process Monitoring. And that's the reason, of course, why you're all here. Just a little housekeeping rule. You're, of course, very welcome to ask questions anytime. You can do so in 2 ways, either write in the chat, or you can also raise your little virtual hand. And then, of course, you're very welcome to speak up when you're invited to do so. That's all from my side. So I suggest, Katrin, I hand over to you if you're ready.
Yeah, I'm ready.
Wonderful.
So, and I think you should see my screen now, right? And the slides. Perfect. Then we can start. So also warm welcome from my side. So today we will talk about a new project we have together actually with, so the TUM has the project together with 9 other partners, and 2 partners are also part of the EuroTech Alliance. So the other research institution who is part in this project, beside of Technion and Technical University of Munich, is TU Eindhoven, and actually our colleague from TU Eindhoven is also in the call. It's Mike. So, and we have a new project with the title Green Additive Manufacturing through Innovative Beam Shaping and Process Monitoring. It has started just 3 weeks ago, so at the 1st of June. And I will describe today the challenge we try to tackle within the project and explain why, for example, we are working together with Technion, who are more on the part of Earth observation. What does this topic has to do with additive manufacturing and green manufacturing technologies? So therefore, the agenda of the talk of today is, first of all, I will give you a short overview on laser-based additive manufacturing technologies and what our challenges are in laser-based additive manufacturing technologies. We will mainly focus on one specific additive manufacturing technology, which is called powder bed fusion, and I will just shortly describe you how the process actually works and what our challenges are. Afterwards, I will just shortly describe describe the idea behind the project, the motivation, and the main innovation we would like to to get out of the project. And afterwards, we will show you some preliminary work we've done at TUM and at Technion in the field of beam shaping. So these preliminary work is, of course, not part of the EU project at the moment, but these were investigations we conducted before in the field of beam shaping. And then I will hand over to Fadi, who will take over the part of multispectral imaging. What is multispectral imaging, and why could multispectral imaging also useful for a production technology like powder bed fusion of metals? And finally, I will sum up the talk with a presentation of all the partners and key facts about our project. So first of all, the motivation. Additive manufacturing. Additive manufacturing is one production technology, and actually additive manufacturing is a term where several, on a technology level, additive manufacturing technologies are summed up. The technology we are talking about today is powder bed fusion. And with powder bed fusion, there are already many applications. One application is, for example, the use case of one of our use case partners, which is Technion, an SME in Spain. And they are actually working together with a rocket manufacturer, Pangea, who tries to design a new rocket system, which is shown here on the picture. And actually that part, this one, and that part in the middle was produced with an additive manufacturing with powder bed fusion technology. And the challenge there was that the material is a copper alloy, and to manufacture this copper alloy is quite challenging. So the idea for the use case partner within our project is that we can manufacture these challenging copper material quite well and in a reproducible way, and we would like to reduce, for example, the costs for the product at the end and increase the production speed. And what you can see on the right-hand side very nicely is that there were also some hot tests of this rocket system at the company Pangea. So this is one use case partner. We have several use case partners for several application fields in automotive, for example, or aerospace application, or in the field of energy. But the idea is, okay, there are already applications, but there are challenges, huge challenges. And I would like now to focus on the process. So what are the process steps and what are the challenges in laser-based additive manufacturing, or rather powder bed fusion of metals using laser beam. On this slide, you see, if you don't know the process and are not familiar with the process, I just described it shortly. So powder bed fusion, I mentioned it, is one additive manufacturing technology where you have a powder bed. This is schematically shown here. The size of these powder particles is really small, around 50 microns, so the thickness of one of your hairs. And you have an energy source. The energy source here would be a laser system. It's a movable energy source with a scanning system, which is schematically shown here. And what is happening? The first step in in powder bed fusion is that you need to apply a powder layer, and this is the powder coating step. And afterwards, you need to fuse this powder layer with the energy input, and the energy input in our case is given here by an IR laser who melts the metallic powder material, and you generate a melt pool. So the project actually is focusing on this energy input step and how to tailor the energy input, but I will describe this later. And the last step is the lowering of the build platform, and then afterwards a new powder layer is applied, and all these process steps are repeated until our final component, who would be the TUM logo here, is created. So that's for those who are not familiar with the process. Now, what is the challenge during processing? The challenge is that we have really high cooling rates. For metal materials, these mean always that the cooling rates determine the the microstructure formation at the end. And we have also, if we have a look on the space, high thermal gradients. And if we now have a look in detail on this process where the laser interacts with the powder bed, you see a highly dynamic process. So this is actually the laser beam, the bright spot here. And what you can see is this highly dynamic process. We have a lot of powder particles flying around, and these powder particles also sometimes interact with the laser beam and with other powder particles, and then you get some kind of agglomerates of the powder particles, and these would be, for example, scrap material later on. Or sometimes it happens that these powder particles who flying around land in the before melting area, which is this one, and creates later on defects in our components. So why is this that highly dynamic process? That's the question. The question we would like to tackle is how to smoothen up this process a little bit, maybe by tailoring the energy input in space, so by a special tailoring of the energy input. But first of all, the challenges. So typically we use for energy input Gaussian beam profile, which means the intensity distribution is like a Gaussian profile. And these leads to defects, component defects or process inhomogeneities like overheating of the melt, which was shown here, spatter and balling effects. I will describe later on what balling defects are. And the aim of our project is to tackle these key challenges. So we would like to bring the powder bed fusion process of metals into a more economical process. So we would like to reduce the production costs by speeding up, first of all, the process, and to reduce, for example, waste material I've described before. So this is another objective, to increase the resource efficiency. Furthermore, the powder bed fusion process is too rich, which means we would like to get a more flexible, adaptive process, and this is done in our project by a beam shaping technology. So the project itself and the idea of green additive manufacturing is underpinned by two technical innovations. The first, and I will describe today, so my part would be the beam shaping part and preliminary investigations we have done in the field of beam shaping, and that's the first technical innovation. We would like to develop an AI-based beam shaping process. Therefore, one of our partners is EOS, a manufacturer of additive manufacturing systems, and they developed a novel optical module where they can on the fly change the beam profile during processing. And we were supported in this area by TU Eindhoven, the Institute of Artificial Intelligence. And the idea would be to get some kind of AI-powered recipe book for beam shapes to create a specific feature on our components later on. And the second part, and actually that's the part Fadi is here today, is multi-spectral imaging. So if we tailor the energy input, we have to understand the temperature distribution, and we have also to monitor the temperatures during processing. And this will be done by multispectral imaging. Fadi will describe the process later on, and also by AI algorithm to enhance the resolution of the pictures we create at the end. And the final aim would be to come in the direction of first-time right production. And I mentioned it, we would like to be more sustainable, increase the productivity level, and, for example, also manufacture materials which are not that easy to manufacture, like the material I've shown you before, the copper material for this rocket element you've seen on the picture von Aenium before. So that's the idea. The project started, I mentioned it 3 weeks ago. So the things I show today are preliminary investigations in the one field, in the field of beam shaping, which came from my side. And these preliminary investigations were conducted with a different beam shaping technology. Nevertheless, the idea is we generated knowledge on beam shaping and the influence of to change the energy input, to change the beam profile on the process behavior. And these investigations who were conducted at the TUM, I would like to show to you today. And the question I would like to raise is, how does this change of the energy input away from this Gaussian beam profile to different beam profiles in powder bed fusion influences processing and maybe also part properties? So what we have done is, and what is known in literature, is that typically we use Gaussian beam profiles, but there are some investigations with fixed non-Gaussian beam profiles, and they have shown, for example, with fixed ring-shaped beam profiles that these researchers were able to create larger process windows, less defects, larger melt pools. So that was the key idea and setting the scene. What we have done in our investigations is now what you can see here is the intensity distribution of a Gaussian beam profile with a high intensity red in the middle and less intensity as blue and these outer rings. And what we have conducted is we used several ring-shaped beam profiles, and you can change these ring-shaped beam profiles on the fly in microseconds during processing. And there are several ring-shaped beam profiles available, starting from this one with the index 1 to the index 6. And what is changing there is that the energy distribution from the middle to the outer ring is visible here, is changed. And at the end, we get some kind of donut-shaped rim profile, which means that the intensity of the energy you bring into your process is more in the outer ring than in the middle with this like Gaussian beam profile you see here. So this was the starting point. And in powder bed fusion, you typically have a specific design of experiments to analyze in which area and combination, typically of laser power and scan speed, so the speed of your laser path at the end, you create a stable processing. And therefore, we conduct a series of experiments, which is shown here for all of these ring-shaped beam profiles. So this means every triangle here is one experimental point, and the other triangles are these state-of-the-art experiment, which is shown here as the Gaussian beam profile. And if we have a look on a typical process window with a Gaussian beam profile, and as material we used a standard material for powder bed fusion, which is stainless steel. And what you can see there, you conduct all of these experiments and analyze later on the welding line. So you analyze on one substrate plate, for example, the welding line and the energy input. And what you can see if you are in a range of a stable processing is that the welding depth is quite similar to the welding width. So this would be the region we would like to reach at the end for our processing. If we increase the energy input, so we increase the laser power, then you are in a region which is called the keyhole regime. It's characteristic in this regime that the welding depth, so this one is way much higher than the width. And this is a process regime which is not favored because the probability of creating porosity in our components is quite high in this regime. So the other process regime is a process regime where you create a so-called balling effect. I've mentioned it before, which means that due to surface tension mechanism, you create some kind like of balling elements on your melt pool, and this is obvious may lead later on to defects in our component. And the last section would be if you have high process speeds and low laser powers, you see that you have some kind of undermelting, so the weld depth is quite low and you're not able to melt one layer fully. So the layer thickness is always around 40 and maybe 80 microns, and if you have a welding depth of less than 40 microns, you're not able to connect your layers with each other. So this is for the standard process using a Gaussian beam profile. What we have now conducted is what happens if we change the beam profile to this ring-shaped beam profile. So this is the ring-shaped beam profile. It's more a donut profile with the index 4, 5, and 6. And what you can see is green is always the process window for the standard Gaussian beam profile. On the y-axis, the laser power, and the x-axis, the scan speed. On what you can see, if you change the beam profile to a ring-shaped beam profile, you can increase the process window, and you are also able to conduct higher process speeds and higher laser powers at the end. And nevertheless, you create a quite stable melt pool. This is something we already published in the paper you see at the bottom. So this was all, everything I shown to you before was only for the one single weld line. But in additive manufacturing, you put a lot of these lines, of these scan passes beside each other. So one scan pass would be in this direction. And what you then see is, of course, an overlap between your different scan passes. And the aim is always to have some kind of overlap, which is around 30%. If the overlap is too high, you have a decreasing process speed, or too low, sorry. And if the overlap, so the distance between your different passes is too high, then you are not really connecting these passes with each other. So you do not only change the laser power, but also the distance between your two different paths. And if you then analyze, so this was the threshold of overlap we would like to reach. So the green area is the area we can work with. And what you can also see is, again, the overlap you create for several hedge distances. Hedge distance is the distance between two lines that you reach with these different ring profiles. For the green one is, for example, a hedge distance of 170. So for more space and a higher distance between these two paths, a stable processing area, which would be in this direction here. And this means, so the distance, you can also increase the distance between your two passes, and this again leads to an increase of your production speed. And the last graph I would like to show to you today on the really results is, again, we have here also our Gaussian beam profile, and we analyzed the melting volume per time unit. And this is also something which shows us that we come in the direction to get a faster processing, which is our aim, to come in the direction to increase the productivity. And what you can see here, the standard beam profile compared to our ring-shaped beam profiles with the different indices, is that you have several parameter combinations where you increase significantly the molten volume per time unit, and this indicates this increase of our process speed. So this was the topic of process speed, but I explained to you the aim that we would like to get a more smooth processing, so a decrease of process dynamics. What you can see in the video in a few seconds at the top is the typical process with a Gaussian beam profile. It's a video video camera which was installed on axis, so you see directly the laser spot here, and what you can quite nicely see is the balling effect here. So these little balls are significant for the balling effect. So it's not a stable process at the end. And now for the same parameter combination, you see the ring-shaped beam profile. And what you can see is that there is an homogenization of our dynamic of the process. So there are not spatter formation and no balling effects visible. And what we have further conducted, so we have seen with our standard diameter of our Gaussian beam profile and ring-shaped beam profile, and what we have conducted at TUM to increase the diameter of our beam profile with an additional zooming axis on our scanning system. So we can zoom, we can increase the size of our beam profile on the parameter of 2. And we can also increase in the focus area the ring-shaped beam profile. And this means that the ring stays a ring. If you are out of focus, you would not have these ring-shaped beam profile anymore. And this means that we can change actually the diameter of our beam profile here from 80 microns around to 420 microns, which at the end leads again to a process, to an increase of process speed. Now you can see on the top video, this is the standard, not zoomed beam profile for the Gaussian one, this one. This would be the video for the for an zoomed Gaussian beam profile. And what you see again are some balling effects. Also for this increased beam profile, you see some balling effects. And for the smaller one, you see also these balling effects. Now we had the same for the ring-shaped beam profile. This is the ring-shaped beam profile in the standard configuration. And on the right-hand side, as zoom configuration, what you have seen is that there's a smoothing of the process, also with this diameter of the ring beam profile of over than 400 microns. So to sum up the investigations at TUM in the direction of beam shaping, only at the moment for rotational symmetric beam profiles. In the process, we will change this a little bit, but I will describe it later on. What we have seen that we increase the process window to come in the direction of a more stable processing. And what we can also see is that we change the microstructure and the solidification line. So this is the solidification line. This is the material which was molten before. And what you can see with the ring-shaped beam profile, that you change the microstructure and the solidification. But to understand this mechanism, we need to understand the temperature and temperature distribution during our processing, because that's the main thing we change. The thermal energy input with this Gaussian beam profile here and the ring-shaped beam profile. And therefore, typically thermal imaging is used. In thermal imaging, the challenge is that you have a fixed emissivity, and this means that the temperature is not the absolute temperature or right temperature. And that was the starting point for the collaboration actually with Fadi, because he's an expert in the field of multispectral imaging. And multispectral imaging can also be used actually to analyze temperatures. If you change it from the more common way in Earth observation, the visible light area, to the IR light area. And that's why I would like to move on and hand over to Fadi now for the topic of multispectral imaging.
Thank you, Katrin, and thank you everybody for attending. I would like to start with a short introduction about imaging in general. I assume that everybody knows what is a digital image that we can acquire with a simple phone or simple camera. So in practice, such an image is stored in the computer as 3 layers. One layer is responsible for the red color, and one other is for the green color, and the third is for the blue color. And there, why we use the term RGB images. So as you can see, it's composed of 3 layers. And these layers actually represent the visible region of the light that we can see in our eyes. So that's why the digital images, trigger ones, has the same, almost the same.
Fadi, can you still hear us?
So he was frozen, right?
Yeah. Ah, Fadi? You were frozen.
And now?
Partially frozen.
So, is it better?
Actually not.
No.
Maybe with the switch.
So if there are already some questions, you can also ask the questions.
Indeed, yeah.
Until Fadi has solved his technical problems, which are common in Zoom meetings.
Hi.
Yeah.
We are from the Metal Institute in the Technion.
Ah, okay.
What machine did you use for the additive manufacturing?
Yeah, actually, this is something. So it's a collaboration between Enlight and Raylace. So Raylace is a scanner manufacturer, and Enlight is an laser manufacturer. And actually, we build up our own system.
Okay. This is how you do the beam shaping.
Yes.
Okay. Yes.
But it's actually an additive manufacturing system with all of the access, but it's self-built due to the reason that it's not that easy to combine these 4-axis scanner with the laser system and do all these controlling. We can hear you, Fadi.
Yeah, now you can hear me?
Yeah.
Thank you. So, okay, so I'll continue from here. Did you hear the introduction about the digital image?
Yes, we did.
Okay, great. So on the other hand, spectral cameras can acquire also light that we don't see in our eyes in the visible range. We usually call it the infrared region, the short infrared region, and the long infrared region. And instead of only a color, we acquire a signature of each pixel in the image, and this signature reflects the properties of the material that we are imaging. You can go on, Katrin, please. Okay, so in remote sensing, actually we use this to distinguish between different materials and map the surface of Earth, and usually the satellites or the cameras from drones or airplanes record the reflected light from the surface, which comes from the sun, hits the surface, and part of it reflected to the sensor, and that's what we measure. And in the next slide, Katrin, please? In the next slide, we can see that in this project we're not gonna measure the reflected light, but it's the emitted light. According to Planck's law, every surface that has a temperature above the absolute zero start emitting light, and this light, the amount of intensity of this light, changes according to the temperature of this body. So that's why if we hit some metal, at some point we start seeing it shining, because at some very high temperature, this reflectance, as you can see here, the reflectance start getting, or the emitting light start being in the visible range, and this we start seeing it. Go ahead, Katrin, please. So here you can see two examples for a simulation of a black body in temperature of 500 kelvins. So the color is really black. We don't have still emission in the visible light, as you can see in the curve here. And on the other hand, also in 1000, we don't see it. But in the next slide, we can see that from certain temperature, the body or the surface start emitting light also in the visible range. As you can see here, it's like in the temperature of 2000 Kelvin, this is the color of the black body, or a body that can very close to black body. And in 3000, it's as really a shiny color. And it's not only black bodies, every surface, especially metals that has this temperature, start emitting this light. And the difference from a black body, the only difference is that we have now also the emissivity. So if we assume, not assume, if we remember that the emissivity for black body is 1, so all the other surfaces on Earth has a emissivity that's lower than 1. So maybe, so that means like that they need more temperature to start shining in the visible region. But in temperatures that we expect to have in the project, in the melting pool, they're above 2000, so we can measure them with spectral cameras. Can you go on, please? So our idea is like to, if you look on the right side, you can see the red signal. It's a signal that we measure from a camera, spectral camera, that can acquire 8 bands in this range between 550 nanometers until 850 almost. So this camera acquires 8 bands and records the flux of the light that emitted from the body in this 8 bands. So we can see this curve, which is the signal. And on the other hand, we can simulate what a black body or a regular body should emit in such, in which temperature the body have to be in order to emit such a signal. So we use this theoretical function through Planck, And as you can see here, we have two unknowns: is the temperature of the body and the emissivity. So the emissivity, we cannot use a single value for the emissivity; it's less accurate. So we assume that the emissivity in each wavelength is a polynomial function. So then we have actually three or four, depends on the degree of the polynomial that we fit to describe the emissivity. And at the end, we need to estimate both the temperature and the emissivity of the material. So for this purpose, we solve an optimization problem, which has which measures the difference between the measured signal in red and the simulated signal according to the Planck's model in blue. So we need to minimize this objective function, and once we minimize it, we achieve an estimation of the temperature and the emissivity of the material that we are investigating. Can you go ahead, Katrin, please? So since we are really in the preliminary stages of the project, we didn't have real data from the process. So we tried it in a different and nice case study. I think everybody remembers the last volcanic eruption in Iceland. So we took one satellite image by a satellite called Sentinel-2 that provides also around 11 spectral bands between around 600 to 2,200 nanometers. And we detected the area where the volcano flow and tried to estimate the temperature of the volcano flow using the same method that we're developing for the project. And now we can see some results. Can you go ahead, Katrin, please? Mm-hmm. Okay, so different from the traditional methods for which called pyrometry for extracting or estimating the temperature from images. Here we can do some more pre-processing, for example, classifying the area that we are measuring or observing. And then instead of estimating the temperature for all the area, for all the pixels, we can save some time, computing time, by classifying the image, because we have a lot of bands. In this case, it's 11, or in our case in the project, we have 8. So this number of bands can allow us for distinguishing between different materials. So we can detect automatically the hot areas. For example, in this case, the most hot area is the one in cyan here that you can see in the area. So we can focus just in this area and maybe a bit surround it, not all the image. So we can save also the computation time. So now here you can see the results. So in the left side is the image, the spectral image or the RGB bands of the spectral image, and in the middle you can see the classification of the pixels. So we focus only on the pixels that are marked with these 3 colors here to save time, and then estimate the temperature only for them instead of estimating for all the image. And here you can see, so according to some literature review that we did, the temperature is very realistic for lava flow after 1 day or 2 days. And a second lava flow that we also tried to detect the temperature there. It's in this next slide. It's another one from the Etna area. Also, again, we can see only the hot areas that we detect automatically through the classification. It's very hard to see it in the visible area, in the visible region. But since we use spectral data, so we can detect it automatically and again estimate the temperature for this area. Okay, with regards to the projects, we wanted to simulate some of the data. So we took one melting area, let's call it, and assume at this point that the temperature is Gaussian distributed surrounding the hitting point of the laser. And we created a synthetic image that should be acquired by the image, the camera that we will use in the project is it's an on-shelf camera. We don't need to develop a new one. It's provided by Sirius, the company, and we can see it in the next slide. Okay. So this camera provides 9 bands actually. 8 bands are in the region between 400 to 850, and 1 band is panchromatic that acquires all the photons in this region. And we simulate an image with this as it was acquired by this image, but this camera. And then in the next slide, we can see that again we divide the melting area into 3 parts according to the temperature, and estimated the temperature for the most hot part. And again, we started with 2,500, the maximum temperature that we simulated here, and we can see that we really estimated very well so far. And last slide, since we are using 8 bands in this case, and we're using optimization problem, not models for some of the rest works that dealing with this problem. The pyrometry, as I mentioned before, are relying on 2 bands only, but in our case, we rely on all the bands, the 8 bands. So it makes our method very robust to noise in the signal. So in the left hand, you can see a signal that acquired, that's simulated with 30 dB, the SNR. And on the other hand, it's only 10 dB, which means like that the signal is very noisy, but still the estimation is almost the same. They are very close to each other, the estimated temperatures and the estimated signals in this case. So we really expect that the new approach for estimating the temperature will really improve the monitoring of temperature in melting pools and maybe contribute to the additive manufacturing. So thank you.
Yeah, thank you, Fadi, for the insights in multispectral imaging and the idea behind it to use multispectral imaging away from Earth observation, coming to analyze temperatures and temperature distribution. So what we have shown today is these preliminary investigations on beam shaping with rotational symmetric beam shapes that I've shown before, and the topic of why we need to analyze the temperature and temperature distribution. What we will do in the project, and this is something new, is that we will come not only from, we are not only able to change from a rotational symmetric beam profile to almost all beam profiles you can imagine. So this would be also some kind of donut profile, some kind of top hat profile, and also beam profiles and intensity distributions which are not rotational symmetric, like these 3 dots here. And this is actually an optical module which were developed at the company EOS, who is also one of our project partners. And within the project, we will get a new system, an additive manufacturing system, M290, equipped with this beam shaping module to analyze what influence the beam shape has, again, on the melt pool dynamics, on the processing behavior, and on the microstructure. And therefore, we need this combination between analyze the temperature, monitor the temperature, and change the beam profile. And this is actually the methodology on a glance of the project. So we have, I mentioned it before, these 2 pillars, AI-based beam shaping and multispectral imaging, and we connect these 2 pillars with each other on one system, so our novel system from EOS. And what is important for us, that we have 4 use case partners. So at the moment, we have 4 partners who are contributing in the area of aerospace, energy, space, and automotive. And we will have, I think, in 2 years, some open innovation competitions. So if someone from industry is here, all these industrial partners are also allowed to apply for these open innovation competition, where you can say, okay, I have a specific use case and I would like to test for my use case your new additive manufacturing technology with these beam shaping opportunity. So that's the methodology in a glance. Here you can see all the partners involved. So we are coordinating the project. Working on the beam shaping technology are mainly the partners TUM, EOS, TU Eindhoven with the topic of artificial intelligence for path planning. We have Technion together with Helios, who are working on software and hardware and multispectral imaging. We have 4 use case partners, BMIT, Amexi, Aenium, and Earlycon for the different applications. And for communication and dissemination matters, we have one partner on board, which is called the BIFOR. Here you can see at the end some key numbers. So all the countries involved in the project, 3 research organizations. I think it's really nice that we have 2, I think it's actually 3 SMEs involved in the project. And it was in the call of laser-based technologies for green manufacturing. So that's the end of our presentation. Thanks to all the audience and also to Fadi and all the other colleagues. Are there any questions now?
I have a question.
Yeah.
To Fadi, yeah.
Yes,
I was wondering about the ground truth that you use for example, for those volcanoes.
Yes. As I said, we just like relied on literature about volcanic eruptions.
On literature, but you were looking at particular images of recent volcano eruptions. So how could you estimate the temperature of those few spots that you have? You try to estimate the temperature.
Yeah, we didn't have like any. It just was meantime visual analysis, and it makes sense so far. And we assume that for the project, for example, in this regard, we need to calibrate sometimes the temperatures.
And how do you plan to do that?
In this case, we must have some ground truth.
So for example, by if you know how hot that heating element is, that is heating that substance, and knowing some kind of physics about some convection, I don't know.
I think you can really maybe calculate what is the expected temperature after 3 seconds.
Yeah, and actually we already sent Fadi data on to measure with multispectral imaging some kind of heating elements where we exactly know the temperature, and that was the idea for the calibration step, as for first step, of course.
All right, thanks.
Thank you.
Further questions?
Nobody dares, huh?
Yeah, you can also write your question in the chat if this
Absolutely, yes.
So okay, so I to fill the gap, I'll ask. Yeah.
So it's our first project meeting, right, Mike?
I definitely would like to give others the chance here, because we will have more chances to talk. But since we're waiting, how do you achieve the different shapes? Is it by means of different lenses?
Yeah, actually, that's the difference between the setups I've shown to you today. So the setup we have used in the past is totally different compared to the optical module from EOS in the future. So the setup we've used is therefore the laser manufacturer actually developed some kind of specific fiber system. So the fiber is the thing from generating the energy to transfer it to the actual scanning system, and they developed something special to change the beam profile. But the setup we will use in the project is different. But this is something the IP from EOS, and I am not allowed to talk about it.
I see. All right.
Okay.
Well, if there are no more questions.
I have a quick question. Can you hear me?
Yes.
Yes.
Yeah. So I was wondering, so you have this printing with the Gaussian shape of the beam, and then you also have the microstructure when you use the ring shape. So I was wondering if then this would be a good way to avoid the elongated grains that sometimes you get when you print along the building direction, because that I know sometimes can cause some anisotropy in the samples. So meaning that you get different properties, for example, tensile properties in the build direction and when you have them vertical or horizontal. So would this be also a good way to avoid that? Because then you don't get elongated grains.
Yeah, I think this is a question we have to tackle. Oh, sorry. So you mean after the video? So this is actually something we would like to investigate in the future, but this is something we haven't done yet. So at the moment, you can imagine if you change the beam profile between 6 different beam profiles, and you have to do parameter studies for all these beam profiles, it's really a huge experimental effort at the moment, and that's why we haven't analyzed these how the microstructure is actually changing. But I think this could be also something which is interesting for the project at the end. But then it even gets more complex, because if you think about complex parts, you don't have any, I don't know, cubes anymore, and then the microstructure in every spot will be totally different. But it could be possible, and within the project, I think, you know it, we already deal we also deal with nickel-based alloys, and they tend to have these grain growth in set direction. So it could be possible, and this is something I think we will investigate in the project.
No, it's super interesting if one can control that.
Yeah.
Thank you.
This means maybe to explain a little bit, to control some kind of voxel-based the mechanical properties of our parts.
Thank you.
Welcome. So, any additional questions? Maybe from someone who is not part of our project.
Yeah, hello. So I will step up. Is there a change in the possible printing resolution? So do you lose how fine you can print the structures because of different beam shapes? And are you worried about it?
Yeah, actually, this is also a topic we would like to focus on. And maybe you have seen it on the last pictures, where we see these different not rotational, symmetric beam profiles. So the idea would also be, if you have really filigree elements, you separate the beam in 3 different beams with one spot actually. And then the topic of resolution and intensity distribution between the different beams, and you separate actually one beam, is important. And this is something we would like also to investigate. And of course, the resolution also depends on the size of your beam profile at the end. But you can imagine we can also create some kind of lines, and not lines, which means shown here, but lines in 90 degree to your actual direction of printing. So it depends on the feature at the end. For fine filigree features, the idea would be to separate it. For other features like volumetric elements, the idea would be, for example, to create future spots or lines and so on.
Okay, perfect. Thank you.
You're welcome.
Sorry, did you change the frequencies of this non-Gaussian shape, or this a shape with some constant frequency?
No, actually, it's constant.
Okay, thank you.
So, further questions?
Doesn't seem like it. But I suppose you, Katrin, and Fadi are also available by email in case someone, after reflection, still has a question.
Definitely.
Yeah, of course. That's why we put here our email addresses. So if you have some follow-up questions, you can write us an email. And for the people from industry, really, in I think 2 years or something like this, we will have this open innovation competition where we're looking for new use case partners.
Maybe we can make another EuroTechTalk then, where you present the results and explain that in more detail. Yeah, that would be nice indeed. Okay, well, if there's no further questions for now, last chance, then I'd say we stop here. I thank you very much, Katrin and Fadi, for your really nice presentation, and also to the audience for attending. And I hope to see you soon then. Have a good afternoon.
Thank you very much. Bye-bye.
Thank you.
Thank you. Bye.
Bye-bye.